Welcome. This video picks up where the last one does in terms of exploring recursion and different recursive recipes. So the next problem we're going to look at is multiplying numbers recursively. Now, this is a spot where we have a better tool, and well, there's a built-in multiplication block that does the job for us. So the goal here is really to understand how we can define this recursively, not necessarily to do the job better. So if we're multiplying 6 times a number, well, 6 times 1 is 6. 6 times 2 really means 2 sixes, 12. 6 times 3 means 3 sixes, right, etc. That's how we define multiplication. Well, if we start looking at this, the recipe for 6 times 2, 6 plus 6, well, really that says 6 plus the answer for 6 times 1. So we could rewrite that as 6 plus 6 times 1. How do we do 6 times 3? Well, we do 6 plus 2 more 6s added. Well, really that's the recipe that we use for 6 times 2. So we could write 6 times 3 as 6 plus 6 times 2. 6 times 4, well, it's a 6 plus 3 more 6s. 6 plus 6 times 3. The goal here, in what we've accomplished, is to kind of come up with a general recipe. How do I do 6 times some number? Well, it's 6 plus 6 times one smaller number. Right, to do 4, I do 6 plus 6 times 3. How do I do 3? 6 plus 6 times 2. This is the kind of thing that we can start thinking about recursively. To take this pattern and write it as a mathematical recipe, we could say that the product of x and y, well, if y is 1, then the answer is just x. Right? 6 times 1 is 6. Well, if y is greater than 1, if we've got a situation like this, how do we do 4? Well, we do 6 plus 6 times one smaller number. So how do I do x times y in general? Well, it's going to be one copy of x plus the product of x times y minus 1. Right? 6 and 3 if my current number is 4. Now this recipe obviously only works for positive values of y. If I start with 6 times negative 2, this is going to keep counting down forever. But as long as we restrict ourselves to that set of numbers, this recipe should work just fine. So let's try and translate this recipe into BYOB code. Okay, so I'm going to make another reporter block. And product of x and y. Alright, so we've got our 2 parameters that we'll use. And every recursive function, I know, is going to have that if-else. So our base case, the thing that tells us we're done, is if y equals 1. Right? Then there's only one more x that we need. We're down to something like, how do you do 6 times 1? Well, it's just 6. Alright, so let's get that in there. So if y equals 1, then we're going to report back the answer is just x. And if you ask me to multiply x times 1, then the answer is just x. The general case, right, how are we going to come up with that one? Well, our answer is going to be the current number plus the same problem done but with a smaller y value. So in BYOB, that'll look like, what's our answer? Well, we're going to report back that you take one copy of the current number and you do this again with the same x and one smaller copy of it. One less copy of it, so one less for y. Alright, so that we'll say go off and do everything from 3 down or 2 down or whatever the next step is. Add that to the current value, and that's our answer. So let's give that a try. Alright, so my product of 5 and 4. Come on. There we go. is 20. All right, to actually see it happen, we'd have to go through the same kind of process of putting some says in, and I'm just going to do kind of one brief one where we get to see what step he's on. So I'm going to use some joins, multiply, and we'll do x, and oops, and we'll join that with y, and we'll join that with that. So multiply x and y. All right, so we can at least see kind of the process he's going through. So he's asked to multiply 5 and 4, which means he's got to do 5 and 3. So he's got to do 5 and 2 and 5 and 1. And once he hits that final level, well, he knows the answer is 5, and he reports that back and gets 5 plus another 5 plus another 5 plus another 5 until he gets his final answer. If you want to, if you're building one of these and you're having problems with it, right, the kind of way to debug this is here's really the meaty part. And if you mess up something in here, it's kind of hard to tell what's going on. So the way to debug that is to make a script variable. And let's call that total for the total so far. And to store that away, so I'd say, okay, let's set the total to be this mess, and then I can report back the total, and I could say the total. You don't really need to break it up like this and have this script variable unless you need to see what's going on. If everything's working fine, then really the version we want is the one that actually just does it and doesn't bother saying anything. So we'll get that one back there, and I don't need the script variable at all or the say. Right, there's my actual recipe. But those pieces can be essential for figuring out what's going on when things don't seem to be working right. So the last recipe we're going to look at is the one for the Fibonacci sequence. And this one's interesting because we can actually solve it with a plain old loop with iteration. And actually that version's probably more efficient, almost certainly more efficient. But the Fibonacci sequence is kind of naturally defined recursively. So the Fibonacci sequence, if you've never heard of it, it's kind of a famous pattern in mathematics. We start with 1 and 1. Those are just by definition the first two numbers. How do I get the third number? Well, I add up 1 and 2. The first two, sorry. 1 plus 1 is 2. How do I get the fourth number? By adding the third and the second. 1 plus 2 is 3. How do I get the fifth number? Well, I add up the fourth and the third. So 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. Each number just comes from adding up the two that come before that. So what does that look like? Well, if the number we're looking at is 1 or 2, then our answer is just 1 by definition. If I'm asked to do the Fibonacci, the third Fibonacci number, so n will be which number we want. So I'm asked to do this one. Well, how do I do that third one? Well, I add up the second and the first. Right? If n is 3, then this says 2, and this says 1. If I'm asked to do the sixth Fibonacci number, this one, then I'd add together the fifth and the fourth, and that would be my answer. Well, how would I do the fifth and the fourth? I'd come right back and say, okay, to do the fifth, I've got to add the fourth and the third. We actually end up doing a lot of the work over and over and over again, but the basic process is sound. So let's go implement this. Kind of once again, the goal is really to just turn this mathematical recipe into the equivalent in BYOB blocks. So let's make a block. It'll be a reporter. The blank Fibonacci number. And let's call it the nth Fibonacci number. So %nth. All right, that'll be whatever, kind of how many steps we want to go. All right, so we know we need the if-else. I know that my ending condition is could be, my base case is this one. It's either 1 or 2, and we could write that lots of ways. All right, I could say if it equals 1 or it equals 2. I could say if it's less than 3. Right, kind of lots of different ways we could say that. Let's go ahead and do the, I'm just going to do the most explicit one. Not necessarily the shortest, but so if nth equals 1 or nth equals 2, then we know the answer is just always 1 by definition. So we will report 1 in that situation. Okay, if it's something else, right, if I'm asked to calculate the 6th Fibonacci number, then I've just got to add together the 5th and the 4th, right? 1 smaller and 2 smaller. So we'll report in the else, we'll add up the, right, and here's the recursive part where how do I do the 6th level? I do the 5th and the 4th. And kind of like the tree, we've got 2 recursive calls. We've got to break this problem up into 2 smaller problems and go do both of those. Okay, so I want to say, oops, get all the way to the top there, and say, if I'm on the nth step, I need to go do the nth minus 1, and I need to do the nth minus 2 step. And when I get those 2 answers, I have to report them back. I have to add them up. So let's try it out. And we'll kind of work our way up. The first Fibonacci number is 1. Second one is 1. Third one is 1 plus 1 is 2. Then 2 plus 1 is 3. The fifth Fibonacci number should be the 3 plus the 2, 5, etc. And these grow relatively fast. If you do, so 10 takes a kind of a second there before he pops out 55. If you try doing a really big number, you're going to be waiting quite a while. The 15, it took that long to come up with 610. So don't go too nuts with this. And the reason why it takes so long is, like I said, we actually end up doing a lot of the work multiple times. Right? How do I do the 15th? Well, I do the 14th and the 13th. How do I do the 14th? I go off and do the 13th and the 12th. Well, I'm already doing the 13th once, so I end up doing that one twice. And it gets even worse as we go down. We end up breaking each problem up. That 13 becomes 12 and 11. And the other 13 becomes 12 and 11. So we do multiple copies of the 12, multiple copies of the 11, and it kind of explodes as we grow the size of the problem. So this is not the most efficient approach, but it is very straightforward and intuitive translation of this algorithm. Now, I'm not going to bother putting the whole debugging chunks in here because mine seems to be working okay. But once again, if something's going wrong, how would I debug this? I'd put in the says to see just like what nth is and make sure I'm counting down. I would break this up into some steps where I say nth minus 1 and nth minus 2 to make sure that I'm getting values that make sense, where I say the individual parts. I say this and I say that one, so the 2 sub-steps. And then that seems, if I get answers that make sense for both of those, then I'd say their sum and basically kind of break it down and just say individual pieces until I figure out what part's not doing what I expect.